Okay, so let's pick up where we left off. I remember just defined the covariant derivative, and I showed you that we have this wonderful proposition that allows us to calculate the covariant derivative. Essentially, we could think of it as telling us the rate of change of the vector field W in the direction of the vector field V. So that is itself a vector field. So in particular, you might notice this equation 2.2, which I have not emphasized yet, but if you look at it, this is, this formula here. You've got VI, partial I, WJ. Well, this is exactly the gradient of W upper J dot product with V. So I don't know if you remember or not from Calculus 3, but that was the formula for the directional derivative. Directional derivative of a function f in the direction V at the point P. Well, we just take the gradient, take the gradient of f, evaluate at P, and dot product with V. So this is not one directional derivative, but three directional derivatives. Directional derivative for each component of the vector field W, and that's what the covariant derivative of W with respect to V is a triple of directional derivatives. And I wrote these on the board, of course, but we didn't have time to prove them, so I want to look at the proof now. And I just would point out here that really what we're looking at is the covariant derivative is itself a mapping. It takes in a pair of vector fields and it outputs another vector field, right? And if you look at this mapping, it's linear. It's additive in both entries, in the V entry and the W entry. It's in fact linear over the real numbers with respect to the second entry because you can pull out a constant. And it's also linear with respect to the real numbers in the first entry. So this would actually give us a bilinear map at each point. Well, anyway, depending on whether you want to look at the vector space of all vector fields or what. But let me not belabor the abstract linear algebra here. And more to the point, the interesting thing is we can pull out a function from the V entry, right? And then, of course, we also have a sort of product rule, which is 5, and then 6, which I don't have a good name for, but 6 is actually quite important. So the proof of these largely hinges on this identity right here. And, well, here's the proof. So let's see here. Proof of 1 and 3. Basically, you got this dot product of UF, U plus FW, FV. And most unfortunate that I've used the letter U for vector field here because we use U as the Cartesian frame, and sorry, I can't fix it at this point. And there's really not too much danger of confusion, but it would be better if I had used a different letter other than U there. My bad. Anyway, properties of the dot product, we've got that. And then you can unravel it into a sum of two dot products summed over. And of course that's the covariant derivative of W with respect to U, and this is the covariant derivative of W with respect to V, which is exactly what we want. If you put if you put U equal to 0, we get just pulling out the F. If you put F equal to 1, we get additivity. So you get 1 and 3 from those special cases. And here's the proof of, 2, 4, and 5. So once more we use the proposition, use additivity. And I had some typos here. This should really be U upper J because this is, unfortunate, but this is the, U is U1, U1 plus U2, U2 plus U3, U3. Here the lower, UI, let's say UJ is partial XJ, right? I mean, that's our go-to notation here. And unfortunately, I mean, it's not, well, anyway, there's a typo there. It should have been U upper J given my current unfortunate choice of notation. So anyway, we break up the sum, and then for this V of wj term, I use the product rule because we're acting on a product of smooth functions, and v is like a derivative, right? So there it is by the Leibniz rule, and then you can put stuff back together. Pull out v of f has got no wj dependence, so I can pull that out of the sum, and like so. Of course, that is exactly w dot u. This is the covariant derivative of u with respect to v. This is the covariant derivative of w with respect to v. Dot product with u, this time dot product with u. Oh, wait a minute. I'm an idiot. Not dot product with u. That's all the covariant derivative of u with respect to v. And that is the covariant derivative, man, that's all I have to say. Covariant derivative of w with respect to v over there. And the f is out front. So there, that for different, let's see here, to get the different cases, you can either set f equal to 1, or, let's see here, f equal to 0, I guess. Well, if f is equal to a constant and u is equal to 0, you get pulling out the constant here. If you put, let's see here. Well, anyway, you can get 2, 4, and 5 from just taking special cases for u, v, w, and f as appropriate. If you can prove this identity, 2, 4, and 5 as given back here follow immediately. It remains then to prove this one. All right, so property 6, key observation here is that the covariant derivative, if it's equal to this, that means that the ith component of the covariant derivative is v acting on wi. All right, so, and again, this is, in some sense, the directional derivative of wi in the v direction, right? Setting aside concerns about unit vectors for a second, right? Calc 3, we insist on unit vectors, but setting aside that nuance of calculus 3, this is straight up a directional derivative of w upper I. Okay, so now I'm working on that proposition, part 6 of the proposition. We let u act on v dot w, and so that's u of this, but then using additivity and the product rule as written right here for u, because u is a differential operator, right? So it obeys the Leibniz rule. So Leibniz and linear gives me that. And then just unpacking things, that is the covariant derivative of u in the v direction. This is the covariant derivative of w in the u direction. The ith component of it, and then whenever you have like II like that for two different vectors, that's a dot product. So this is the dot product of the covariant derivative of v with respect to u with w, and the dot product of v with the covariant derivative of w with respect to u. There you go. And that's 6. Now, of course, I said these calculations should all be understood to be done at a point P, but the cool thing is we don't have to write the P because omitting it doesn't really lose anything. In fact, I would say that's one of the main advantages, in some sense, of this proposition back here, right? Like this, once we got to that proposition, we haven't really written the point dependence much after it. Of course, the definition of covariant derivative necessarily involved the point dependence because we had to, evaluate the vector field W at the curve and differentiate. But now we've gotten away from that, so we can think about vector fields. I think you've seen from the homework that sometimes it's actually much trickier to work at a point in practice than it is to work with functions. It's funny how that is. But in any event, here is a nice formula for the covariant derivative that we can use in practice to actually work examples out. The covariant derivative of W. My son Benjamin has come to join us. So the covariant derivative of W with respect to V is V on W1, U1, V on W2, U2, V on W3, U3. These are those three directional derivatives I talked about. And that gives us the change in the U1, the change in the U2 direction, the change in the U3 direction of W with respect to V. So this next example I just go ahead and I calculate the change of W1 in the v direction, the change of W3 in the v direction as this and that, just by calculating directly, and then I put those together. In this example, W2 is 0, and so putting that together, we get the covariant derivative by adding together those different directional derivatives, like so. And there it is. It broke.
Nothing broke on you.
Nothing broke. You're not breaking my car, are you?
It didn't fall and not broke.
It just fall done broken. That's good.
It was not broke.
Okay, good. Now you told me you were gonna not be. You told me you're not gonna make noise, because I had to start this video over again.
I didn't talk.
You didn't talk. What are you doing right now?
I was falling and make sound.
Oh, you just fall to make sounds, huh?
Yes.
Okay. Well, I'm gonna keep making my video.
Okay.
Okay. So this example, Audric, is I think answered partly your question about what's geometrically going on here. This starts to give an answer to that. I think the answer I just gave about it being directional derivatives may or may not be satisfying. It kind of depends on how much of an intuition we have for directional derivatives, right? But this does reveal something. If we look at calculation of the covariant derivative of v with respect to v itself, my initial thoughts on this would be that would be 0 because v doesn't change in the direction of v, right? But after I go through the calculation here, let's see what happens. So v dot v is the length of v squared, right? So if f is the length of v, then since v acting on f squared is 2f gradient of f, v of f, by a chain rule we had, that means that v acting on v acting on the length, v acting on the length of v squared would be 2 times the length of v acting on, the length of v. So much writing. So many v's and bars. It's hard to see what you're doing, right? But there it is. On the flip side, if you look at the right-hand side right here, this is twice the covariant derivative of v with respect to v dot v. So that brings us to 1/2, bringing the 2 over here to there. And then v acting on covariant derivative v squared is 2 length of v acting on length of v, right? So it gives us this identity. And then if we divide that identity here equal to that, if we divide that by the length of v, we get this guy over here, which is pretty neat because it says that so this right here is the unit vector in the direction of v, right? And so this says that the component of the covariant derivative v in the v direction is given just by v acting on the length of v. So in particular, if the length of v is constant, then the covariant derivative of v in the v direction is 0. So that was my intuition, partly because we've been thinking about Frenet-Serre equations in the TNB frame. Those vector fields have constant length, right? So like the covariant derivative, if we were to calculate covariant derivative of b in the b direction, that would be 0, etc. Or t in the t direction. All those are 0. Now, one of your homework problems explores the covariant derivatives of the Frenet frame, not exactly in that sense, but this problem 8 is actually related to this discussion, because problem 40, which is problem 8 of section 2.7 of O'Neill, actually asks you to look at the covariant derivative of the Frenet frame. And so that homework problem will connect back partly with the discussion we're having at the moment. But in order to properly understand it, we need to get to connection forms, and I haven't said hardly anything about that yet, so let's get on with it here. Okay, so one final comment: covariant derivatives are interesting, and they will continue to be interesting as you study more higher math. There's something called a fiber bundle, where there's some notion of covariant differentiation, and it ends up tying into like modern physics, gauge theory. If you want to study generalizations of electromagnetism, where your gauge group is not just U1, you end up needing to look at a fiber bundle where the gauge group well, sections of that gauge group tie into the story of covariant differentiation. You need covariant derivatives and these fiber bundles to properly frame the mathematics there, although I'm using frame in the more the metaphorical rather than the technical orthogonal sense here at the moment. Okay. So, section 2.6, frames and connection forms. We've actually kind of started into this already, in the sense that we looked at the attitude matrix earlier in the chapter, and this is somewhat related to that. But well, we'll get back to the attitude matrix is all I'm trying to say, okay? So if we have a frame, which is, again, a set of vector fields, which is what? Pairwise perpendicular and length 1 for us, then, in other words, EI dot EJ is Kronecker and delta IJ. If we have that condition for a triple of vector fields, then they're a frame. If in addition we have that E1 cross E3, E2 is equal to E3, then it's a right-handed frame, which is actually, these two things are pretty much assumed in O'Neill. When he talks about a frame, he's talking about a triple of vector which obeys both of those conditions. It's orthonormal and right-handed. And in any event, if you have such a triple and you expand it, a vector field with respect to that frame, then these component functions with respect to the frame, well, they're generally functions, and you can get them by taking the dot product of v with ej. All right. And it's interesting, as we looked at, in fact, in class, to expand the covariant derivative in terms of such a thing. And so I go about that calculation. We kind of did this in class, but I'll go through it again here. And so suppose v and w are vector fields, and we're expanding v and w with respect to this frame, E1 through E3. Then we have this. We can pull the sum out because of the properties of the covariant derivative. We can use we can pull the f's out because they're in the first component. We can do the product rule because it's g times g and ej are both, well, that's the product rule for the covariant derivative. And there it is. And then putting the f and the e back together, that gives us the v. Notice the sum over I is gone there. And over here, we have sum over I and j, f upper I, g upper j, covariant derivative in the EI direction of EJ. And at this point, I recognize in the notes the need to define the connection coefficients. Well, actually, first I stop and smell the roses and notice like how this formula drops back to the proposition we started with today. If you have EJ equal to UJ, the covariant derivative of UJ is 0 because it's a constant vector. And so like this term drops out when we're working at the Cartesian frame, and we just have that. So like for the Cartesian frame, we just have this formula with EJ being UJ and that being the Cartesian component function, right? Again, not to beat a dead horse, that was that very exciting Luther. It was the very useful proposition 2.54. That's what this formula looks like in the Cartesian frame. But in the non-Cartesian frame, we get these other interesting twisty parts over here that have to do with what are called the connection coefficients, as defined here. So, actually connection forms. And I do mean form in the sense of differential form, in the sense that a differential form in O'Neill was defined to be a linear map on vector fields. So like phi is a differential form means that phi is a mapping from vector fields, all right, to the reals, which, well, I guess it wouldn't be to reals. It would be to smooth functions, I suppose. If we put a point, if we did it at a point, differential form at a point, then it would be from the tangent space. It would take vector out and it would spit out a number, right? That would be differential 1 form. And these are in fact connection 1 forms. And they're defined as follows. The omega ij is equal to the covariant derivative of EI in the v direction dotted with ej. And this is, of course, all at the point P. As I was saying here, omega ij jp is a covector. It's a covector in TP R3 star, the cotangent space as we called it. And if we look at the assignment of a covector at each point in space, then that gives us a one form, a differential one form. Again, it's by the assignment P goes to omega ij of P, right? So with this in mind, I showed you in class, and I'll show you again as soon as I find my next page. We can, what can we do here? Well, if E1, E2, E3 is a frame, then omega ij is equal to minus omega ji, and the covariant derivative of ei in the v direction is omega ij of v acting, times ej. I think I may have used this proposition in class, and so now I'll look at the proof. The proof is, it rests on essentially, it's by property 6 of the covariant derivative, essentially, which I think we use in example 2.57, but 6 here says that, the u acting on dot product is that. So if we put v equals to ei, w equals to ej, and v as being my u there, so we have covariant, let's see if I can put it, let me try to get it so we can see it all. So let's see here, like v is playing the role u does there, all right? And we have covariant derivative of v, since u is playing the role v, right? Covariant derivative of v over here. And the v is ei and the w is ej, like that, all right? But this by definition is omega ij of v, and this by definition is omega ji of v. To see that directly, we're using the commutivity of the dot product, which says that this is del v ej dot ei, right? And that by definition is omega. Oh, I've lost my definition sheet. Where'd you go? Oh, my papers are all out of order. Where'd you go? Ah, here it is. See, omega ij of v is omega del v ei dot ej. So del v ej dot ei, that's omega ji of v. Which is why I said that this term right here was omega ji of v. So anyway, what we have is that the, zoom out a bit here so I don't end up, see better. So what we have, of course, is that omega ij is equal to minus omega ji, since that's true for all v. Okay. Now, finally, this is literally the jth component in the E frame of covariant derivative of v of ei, so this follows immediately because we can remember, like we were doing the proofs earlier in class, every vector we have we can expand by dot products with the basis. Well, we're just using that here. This is the jth component of that. Rather, this is the jth component of, good grief, the jth component of this. So I can add the first plus the second plus the third multiplied by E1, E2, and E3 respective to build back that. So that's where that formula comes from. All right, and let's see here. Oh, okay, yes, this is just what I just said, but I'm giving it a name. Call this thing W. This is a general identity. W is equal to the sum over J of W dot EJ EJ. So this is equal to that, because w dot ej is literally omega ij of v. Okay, I think I used that in class, but of course we hadn't proved it. It is very nice to notice that the covariant derivative of v in the E1 v of E1 is given by omega 1, 2. I do believe there is a mistake here. Let's see here. Yes. So this proposition right here said what? Some omega ij, ej. So the j on the omega has to match the ej there, right? So down here, that is a typo. That should be not. Come on. So that is not omega. Excuse me, that is not E1. That is supposed to be E2. Okay? E2. And, right. Now, think about this. We knew I would expect that there is no component of the covariant derivative of E1, E2, or E3 in the respective E1, E2, or E3 direction. Why? These are length 1 vector fields. We have already shown in that previous example that the covariant derivative of a length 1 vector field has 0 component change in the direction of itself. So it must be that these have only, like 1 has to change into the 2 and 3 direction, 2 has to change into the 1 and 3 direction, 3 has to change into the 1 and 2 direction. Another way to look at this is actually by the previous proposition. We just had that omega ij is equal to minus omega ji. What does that say about omega ii? That's equal to minus omega ii, right? In other words, omega ii equal to 0. So we know that when we look at the connection coefficients, we're only going to have distinct indices like 1, 2, 1, 3. So when I look at the covariant derivative of E1 in the v direction, I'm going to have omega 1, 2 and omega 1, 3. But I'm not going to have an omega 1, 1. Down here, I'm not going to have an omega 2, 2. Down here, I'm not going to have an omega 3, 3. Right? And okay, so the reason for this minus is that this, if I can write over here, the covariant derivative of v in the E2 direction was equal to omega 2, 1 of v E1 plus omega 2, 3 of v E3. And then notice that to rewrite that as minus omega, to write that as omega 1, 2, I have to flip the indices 2 and 1 to 1, 2. That's where the minus comes from. And likewise down here, to get 1, 3 and to get 2, 3 there, well, originally we would have had, using proposition 2.62, which is right above, we would have had like omega 3, 1, E1 plus omega 3, 2, E2, right? That would have been covariant derivative v E3. If you don't mind, I'm gonna press. Fine, I'll put it back in of the so obnoxious. Sorry, hardly fits. Anyway, in other words, to get 1, 3 and 2, 3, we had to switch the order. That's why there's minuses here and here. Okay. Now, what else? Well, we can arrange the differential form omega ij into a matrix. So partly I'm rewriting all of these things up here. I'm purposely using 1, 2, 1, 3, and 2, 3, and avoiding using 2, 1 and 3, 1 and 3, 2. because I want to show you that you can write the matrix just using these three forms. Three one forms. This is a matrix of one forms, in fact. So omega 1, 2, omega 1, 3, omega 2, 3, minus omega 1, 2, minus omega 1, 3, minus omega 2, 3, like so. And indeed, this is a matrix of one forms. So I keep saying we're going to get back to what I did in class. We will eventually get back to it. We're not there yet. So what I did at the end of class was kind of in class, part of in class. It jumped ahead a bit. So sorry about that. Anyway, so now that we've discovered there's a natural matrix of one forms connected with these, well, connection coefficients, we stop and spend a couple minutes on, like, what do we mean by a matrix of forms? And so it's relatively simple. Essentially, we just combine the matrix multiplication and addition with wedge products and just try to do it together. And I mean, this is the essential definition. To take the wedge product of two matrices of differential forms. First of all, I assume that the two matrices have forms of the same degree, like A is a matrix of one forms, or B is a matrix of three forms. I'm not going to have A is like partly made of one forms and partly made of two forms. Like, it has to have homogeneous degree throughout all its entries. Now, these could even be zero forms. Like, if A and B are both just matrices of functions or matrices of numbers, then this drops back down to ordinary matrix multiplication, and typically you would omit the wedge, right? And likewise, we define the exterior derivative by taking the exterior derivative. The exterior derivative of the ikth component of a matrix is the exterior derivative of the ikth component itself. I also, in this section, make use of the standard basis matrix EIJ. So, like, for 2 by 2 matrices, just so you know what I'm talking about, E11 is 1, 0, 0, 0. E12, 0, 1, 0, 0. E21, 0, 0, 1, 0. E22, 0, 0, 0, 1. These matrix units are super nice. You can build any matrix as a linear combination of these guys, so they're useful in the study of sort of abstract matrix theory. I think I have an example here. Let's look at the example. All right, so here I have A is this matrix of one forms, B is this matrix of one forms. I take the wedge product of the two matrices, and to do that, we just multiply them like they're numbers, but the multiplication becomes wedges. So to multiply, let me just kind of do some circling. Typically, I think about taking dot product of the column of the right factor with the row of the left factor to get an entry like this one. And that's what I did here. I took dx wedged with dx plus dy times dy plus dy wedged with z squared dy. And so if you sort through this, it's really just the usual matrix multiplication where we do wedge products instead of multiplication, but otherwise it's kind of the same song and dance. To take the differential of these matrices, that's easier because, like, remember d squared is 0, right? So since d squared is 0, d of dx is 0, d of dy is 0, d of dz is 0, and you just got the differential of this guy. So you get, 2z dz wedge dy plus 2y dy wedge dz, and I just rewrote it in one. I made it both dy dz, so that put a minus on this one because I had to switch the order of. Put a minus on this one because I had to switch the order of the dy, the dz and the dy. And likewise here, these differentiate to 0, exterior differentiate to 0, and this just gives us 2z dz wedge dy like I have down here. Right? And notationally, you could also write these, like, is it a matrix of matrix of two forms, or is it a two form times a matrix? I mean, you can kind of go either way. We could reasonably write this as 2 times y minus z, dy wedge dz times the matrix 0, 0, 2, 2. Oh, come on, dude. Really? 1, 0, right? This is a typo. My apologies. That should be 2, 1. Goodness gracious, I'm glad we talked about that. Wait a minute, was this dB? This was dB. Oh, I'm an idiot. That's dA. I can't even. I just can't even. All right, so, yeah, that's 2, 2, isn't it? So sorry. All right, anyway. My inability to read my own notes aside, I hope that example makes sense. But we also have, you know, the product. This is actually something we'll use soon. The exterior derivative of the wedge product of two matrices of differential forms is the exterior derivative of the first matrix, wedge the second, plus minus 1 to the p, a wedge dB. So here we're assuming A is a matrix of p forms. And I proved this result for you for like you might say a scalar valued form. So the differential forms we looked at before were just, you know, they weren't matrix valued, right? These are, but it's still true because the exterior derivative of the ijth component is the, excuse me, how to say this, the, so this would be the, if I took d of a wedge b, right, and I calculate the ijth component of that, by definition, that is the exterior derivative of the ijth component, which is this by definition, which is then because of linearity of the differential that, and then because of proposition 1.33, which we proved in class like last week, with all that horrible multi-index notation stuff, we get that. And then going back, that's dA wedge b plus minus 1 to the pa wedge dB. And it's the ijth component. And since this holds for all ij, we conclude that dA wedge b is like we want. So it's kind of shocking to me how easy it is to prove things about matrices of differential forms. But there it is. Now, we had before talked about the attitude matrix, all right? And we proved that the attitude matrix was orthogonal in the sense that A transpose A equals I, right? So if we think of a regular matrix as a matrix of zero forms, then we might write A transpose wedge A equals I, just to emphasize it's really part of that story. It's just the zero, wedge zero is another zero form. It's kind of silly, but there it is. And but the larger point is that this identity up here holds in the case A and B are both zero forms, just the same. And so because of that, we have this attitude matrix proposition, which is that dA transpose wedge A is equal to minus A transpose wedge dA, and likewise dA wedge A transpose is equal to minus A wedge dA transpose. Or more to the point, we can write the exterior derivative of the attitude matrix simply as minus A wedge dA transpose wedge A again, which is kind of neat. Now the proof of that is almost immediate from the proposition which follows, but I'll go through it. So we have A transpose A equals to I, so we differentiate that. And when we differentiate that, we get dA transpose wedge A plus A transpose wedge dA equals to dI. But I is a constant matrix, so dI is just 0. And similarly for the other multiplication, we have that. And so that's 0. So that gives us this and that. And if you multiply, remember A, again, A transpose is the identity. So if you take either one of these and like wedge it with, I said multiply this by A on the right, then you get, if you multiply it by A on the right, you get, I'll write out here, dA wedge A transpose wedge A, multiplying on the right, right? Equal to minus A wedge dA transpose wedge A. So let me just do some color coding here. So this was what we had. So I'm doing this part and that part unaltered from that. and I'm just taking the multiplying by a on the right there, wedging with a on the right. Then when you do that, A transpose A wedges to the identity, and the identity matrix wedged with anything is just the matrix again, so that's dA is equal to minus A wedge dA transpose wedge A. And there's the one of the claims. Yeah, as I said, I invite the reader to show that dA wedge I is equal to dA. I mean, I invite the reader to show any matrix wedge the identity matrix is the matrix again of forms. But okay. Any of that. Here's the theorem we get from that, among others. And if A is the attitude matrix of a given frame, then in fact the connection coefficients of the frame are given by dA wedge A transpose. So just to remind you, at this point you might be like, well, I don't remember what the attitude matrix was. Well, that's understandable, but here it is right here. So the attitude matrix was formed from the components we need to expand the frame in the Cartesian frame, right? So the attitude matrix is essentially defined right here. This is what defines the attitude matrix. It's the coefficients you need to expand the frame in the Cartesian basis, right? And so there it is. And the definition of omega is right here, okay? So let's calculate. So we calculate omega I j of v. I'm going to zoom in a bit here. Sorry if it's fuzzy, I need to get some lens cloths or something. Omega ij of v is, well, covariant derivative of v of ei, which is this, right? But I've taken the liberty of expanding ei in terms of the attitude matrix, right? Dot ej. Then I pull the sum out, because that's a property of covariant derivative. Then I use property, I forget, 5 maybe of the covariant derivative, and it's essentially the product rule, which says that's the covariant derivative, that's v acting on aik uk, plus aik covariant derivative of v acting on uk. But remember, uk is that constant vector, so we know that this is straight up 0. That piece is 0. So what's left is this dot that. Now, uk, but ej is what? Well, ej is literally, this guy is that business. We can expand ej in terms of the attitude matrix as such. And so then we have this dot product. We pull the sum over L up front. The VAIK is still there. The AJL pulls out to there. And notice that UK dot UL is Kronecker delta L, KL. As I've discussed with you, the Kronecker delta is the natural enemy of the finite sum. It's going to kill one of them. Which one is it going to kill? I chose to kill the sum over L. And so everywhere there was an L, it has now become a K. So where do we go? AJL becomes AJK, and AIK is still AIK. We got that. But what is that? That is exactly by the definition. So, okay, so this, one more step. This is equal to the sum over K of V of AIK, AK, A transpose KJ, A transpose KJ. So that flips the indices, and now we have the matching K up like we want, and then now it's the product of VA with A transpose as desired. And to be clear, what we mean by VA is this matrix of functions down here, and in fact, that is exactly, as we've talked about, we can either talk about dA12, but that by definition is dA11, or the V of A11. That's dA11 on V, and so forth. So this V of A is dA of V, which is kind of cute, right? I mean, we did this for functions, now we're doing it for matrices of functions. There it is. That is then dA of V A transpose, if I can find the next page. And in view of the fact that this, this is literally dA of V A transpose, right? IJ. Since this holds for all V, sorry if I can get, I don't know if I need to. Get cameraman in here. All right. So since this is equal to that for all V, it follows that omega IJ is equal to dA wedge A transpose. Since it holds for all V, we can drop the of V. But understand that the way this one form acts on V is for dA to act on it. That's incidentally part of the deal here. But in any event, there it is. And I actually have some examples here. So let's see here. We had this attitude matrix before for the cylindrical coordinate frame. If you calculate dA, you get that. And so if we calculate dA wedged A transpose here, we end up with this rather nice, simple little formula over here. 0 d theta minus d theta 0, 0, 0, 0, 0. And again, as I said, the connection one form, it is a one form, it's a matrix of one forms, and there it is. Now, this one, I am leery of my pluses in here. I remember that we made a correction in class. I need to go back and look at that and redo this in light of that correction. I probably should have made that a homework problem, honestly. But that would be a good exercise to do. Go back, find our corrected attitude matrix, because we found the attitude matrix for the spherical frame in class, and I think we found it pretty carefully. And so take that attitude matrix, calculate its exterior derivative, and then multiply by the transpose of that, and we should get something. We'll get something like this up to a sign. It ends up having a d phi part and a d theta part, like so, something like that. Although I think that I'm a little bit leery. I'm leery of this example. I feel like this may have the theta and phi interchanged from the way we used it last time in class. In other words, if you're confused about this example, don't be too worried. I'm also very leery of it. I need to fix this. I'll try to fix this. Make an announcement. Now I have homework. Good job. So, okay. That brings us to section 2.7. And so this is on coframes and the structure equations of Cartan. And I think that I would like to talk to you guys about this stuff in person. So I think I'm gonna pick up again here in class next week, and I think if I'm disciplined, we'll make it through chapter 3 and this next time we meet. So again, sorry for my poor planning. I'm still working out the kinks here. Eventually, I'll get it together. I think this is going to work better to not have me try to make cogent sentences for 4 hours in a row. So I think at most I'm not sure I even have 1 hour cogent sentences. But anyway, hey, have a good weekend, you guys. Thanks.